Okay, this is a problem that we talked about in class. We have a rocket that's made up of three surfaces here. Um, the first two problems is asking us to parameterize a surface and to sketch the graph. So let's take a look at this. First one is a cone, and it's a cone that's that has a tip at 10 and it's upside down. And so we're going to parameterize it using polar coordinates. Let's call it phi of r theta in polar coordinates. Let's call it phi1, so that will refer to the first surface. And then our x is going to be r cosine theta. R sine theta. And our z is 10 minus x squared plus y squared under square root. We know that x squared plus y squared in polar coordinates is r squared, with a square root is just r, and we are talking about the positive side, so that's our parameterization. Now the r limits are going to go from 0, that's at the tip of the cone, and then it's going to have to stop off at 8 when z is equal to 8. So imagine this was 8. So we have square root of x squared plus y squared is equal to 2, and x squared plus y squared is equal to 4. So the radius is going to be 2. And then our theta goes all the way around from 0 to 2 pi. A good thing to do is use a graphing program to plot this to make sure that we do in fact get this surface. So the surface would look like this, up the z-axis at 10, and then down here z is equal to 8. So that's the first surface. The second surface is a washer. So this is basically a disk with a hole in it, and it goes at level z is equal to 8. So let's call this phi2. We can use r and theta again, because this looks like a polar coordinate washer, and we'll keep the same x, which is r cosine theta, and the same y, which is r sine theta. And this time, instead of having our z change, our z is going to be fixed at 8. The r, x squared plus y squared, r squared goes from 1 to 4, and so r must go from the square root of 1 to the square root of 4. And then our theta is going to go from 0 to 2 pi. So at level 8 here, we have the disk with a hole in it, and so this is our second surface. Now that cone was open, but and it still is open. We capped it up, but we didn't cap it with a closed disk. We capped it with a washer, which means there's still an opening down here. Let's see where the third one takes us. Our third one is a cylinder. X squared plus y squared is equal to 1 from 0 to 8. So our phi3. Now this time we have x squared plus y squared is equal to 1. So that's going to be a fixed radius of 1. So I'm not going to use polar coordinates anymore. But I do want to create a cylinder, and usually we include a theta that makes that can have us take things all the way around, and then we would need, this thing is going to range from z is equal to 0 to 8. So let's have a z as our second parameter. So we have a fixed radius of 1. We don't need to put that 1 there, but I'll just put it there anyway. So it's 1 cosine theta, 1 sine theta, and then our z is going to range, and in fact is going to be our second parameter. So theta is going to go all the way around from 0 to 2 pi, and our z is going to take us from 0 to 8. So this is the level 8, and then we just have to drop all the way down to 0. We have a cylinder, radius 1, and here is our rocket. So if we were to draw our axis, this is our z-axis. Our x-axis would be all the way down here, and then our y-axis would be over here, and this would be inside of that cylinder, passing through the washer, inside the cone, and then popping out there. This has radius 1, and over here is a value of 2, radius 2. Okay, this is our rocket. Here's our rocket. The next question is we have a vector field here, G, and they want us to compute the flux of the curl of G over this whole surface with an outward orientation. So we didn't really talk about the orientation there, but outward orientation, depending on which surface you are on, would look something like this. So if we were to do this directly, well, first of all, let's write down what we need to do. Let's say this whole thing is S. They want to compute the flux of the curl of G so if we were to do this, we would need to break this up to 3 surfaces. S1, S2, well, I guess this is S1 over here, S1, this is S2, and the cylinder is S3. We need to take the curl of this and then take the flux over each of these 3 surfaces, which will take quite a while, I am assuming. But if instead of doing that, we take a look at Stokes' theorem, and with the right-hand rule, we're going to have rotations going this way along the normal vectors. So Stokes' theorem will exchange, will trade we'll trade in a flux integral for a line integral. And for the line integral, we need to figure out our boundary. This looks like it's our boundary down at the xy plane, and we just need to figure out our orientation. So if the x-axis goes this way and the y-axis goes this way, this looks like it goes from positive x to positive y in that direction. So it looks like we are going in our positive direction, which is going to be the counterclockwise direction. This is a circle of radius 1. And so what we're going to do is we're going to exchange this flux integral for a line integral over a closed loop going in the positive direction. And this is the boundary of S, and now we're just going to take the original vector field G and go for that line integral. Okay, so it looks like it might be important for us to parameterize, give a parameterization for our boundary of S, and so this parameterization is just your standard 1 times cosine of t, 1 times sine of t, and then we're flat on the xy plane, so it's going to give us a 0. We also will eventually need the derivative, so it's negative sine of t, cosine of t, and 0 again. Alright, so what we need to do to get our working definition going is we're going to need our parameterization. Let's include our limits so that when we set up our integral we can include our limits here. So we need g evaluated at r of t dotted r prime of t dt, and let's figure out what g dotted or g evaluated at r of t is. So wherever I see an x, let's put in a cosine t. Wherever I see a y, put in a sine t, and 0 for z. So it looks like for our first component it would be 0. Our second component is a cosine, so let's call that cosine squared t. And our last component, let's see, there's going to be a big mess. I'm just going to put star here because I'm looking at the derivative, which is what I'm going to dot it with, and I see that the z component is 0, so it didn't really matter what's going to go here because it's going to get dotted with 0. So we got negative sine t, positive cosine t, and 0. And when we take this dot product, we see that 0 and sine t go away, 0 and star, this big old mess over here, will go away, and we just have a cosine cubed. Alright, so let's see, without a calculator, we'll need to do a simple u substitution here, so let's just do the calc 2 work or even calc 1 work that we need for this. We'll split this up to cosine squared t times cosine t dt. Let's see that cosine squared t will become 1 minus sine squared t, cosine t dt, and then this is going to prompt me to do a u substitution where u is equal to sine t, and then du is going to equal to cosine t dt. So there's my du, and I have 1 over u squared, or 1 minus u squared. So then my integral then would become 0 to 2 pi. These are t limits, and I'm going to go 1 minus u squared du, and this will give me, I suppose we can change our limits also. I guess this is what's going to happen. If u is equal to sine t, our limits are going to be u of 2 pi, and that's sine of 2 pi, which is equal to 0, and u evaluated at 0 is sine of 0, which is also 0. So I guess with the u limits here, u is going to go from 0 to 0, then we can just be done here and say that the integral is going to be 0. So that's the first one. It looks like the flux of the curl of g over this whole surface with an outward orientation is 0. That's because we actually took the line integral and we got it to equal to 0. Now let's take the same set of surface, and we have a new vector field f. We want to compute just the flux of f over the surface with an outward orientation. So the flux is a double integral over a surface, and that's a vector ds with a capital S. as in a surface component. So what we want to do is, well, if you're thinking ahead over here, it looks like if we take the div of this would be a nice easy function to take the div of. Um, so unfortunately this is an open surface, but again we can remedy that. We can close this surface off by adding this disk here. So with that open surface, if we add double integral of a disk, let's call this S1, over, so we're taking the flux of this vector field over this S1, and then if we add on the flux of the vector field over the whole S, this whole thing is S, the three components, or the three surfaces, then we now have a closed surface, and according to Gauss's theorem, this is going to be, or this can be replaced with a triple integral over E, where E is going to be the collection of these, the solid that's enclosed by these surfaces of the div of f dv. So it looks like we're going to be interested in finding these two integrals to be able to solve for this. So it's going to be this integral minus this integral is going to equal to our original integral that we were looking for. Alright, let's see. Let's do the div first. And it looks like it might be a good idea if we figured out the div of f. And the div of f is a scalar function. The derivative of the first component with respect to x, there's no x's there, so that's 0. Derivative of the second component with respect to y, no y's in there, so that's 0. Derivative of the third component with respect to z, looks like that's a 7. So the div of f is 7. That makes a nice setup for us where we have a triple integral of 7. So that 7 is a constant. I can go outside and so we're just simply looking for the volume of these things. Well, that's going to be 7 times triple integral over, let's call this volume of the cone, E1, and then we're going to need to take a look at the solid cylinder. Let's call that E2. So these triple integrals we won't need to compute these triple integrals, we just need to find the volumes of those solids. So let's take a look at this cone. This cone goes from 8 to 10, so it has a height of 2, and then the radius out here, we figured that out, and that was 2 also. So the volume of the cone, V of E1, is going to be, the volume of the cone is 1/3 pi r squared h. Well, what's r squared? R is 2, h is 2, so that would be 2 times 2 times 2. It looks like it's 8 pi over 3. So that's the volume of E1. E2 is a cylinder, radius 1, and the height goes from 0 to 8. So the volume of the cylinder is going to be the area of the square, pi r squared, times the height, which in this case is 8. So we get 8 pi. So what we have here is for E1, the cone, we have 8/3 pi plus 8 pi. So it looks like it's 24 plus 8, that's 32. Oops, not equals, it's times 32 pi over 3, and then I'll just multiply that by 7. It doesn't look like we're going to cancel the 3 out anywhere. So 7 is 14, 21, 22. So this is the triple integral here. Now we need to take the flux of this thing. So let's see if we can figure that out. With an outward normal, the normal for these flux, the flux integral over the surface will give us a downward normal. So let's call that normal n, going from 0, 0, 1. That's your normal vector. And so let's replace this flux integral in this form, and let's say f dotted with n ds, and now my s doesn't have an arrow because then we took that normal component out. Now, whoops, that's not a triple integral, it's just a double flux. The f is this function over here. Now looking ahead at my normal is 0, 0, negative 1. Well, that 0, 0 tells us that it doesn't matter what's going to be in the first two components. The only thing that would matter would be in the third component, so it's just 7z. But remember that this is a double integral, so we need to identify our parameterization so we can replace it with z, replace z with that. So let's call this parameterization, I think those three surfaces were 1, 2, and 3, so let's call this 4. And it's a disk, so let's use R, and whoops, no arrow there. Let's use R and theta, and it'll be R cosine theta, R sine theta, and we are flat on the xy plane, so z is equal to 0 there. R is going to go from 0 to 1, and theta goes all the way around to 2 pi. So here we go, z is equal to 0. Well, z is equal to 0, it looks like this whole dot product is going to be 0. So 0 for those stars, and the last one that would have had the only chance to become non-zero is going to be 0 after all. So whenever you have a single integral, a double integral, a triple integral, a surface integral, or in the path integral where the integrand is 0, then the whole thing is just going to equal to 0. So back to our equation, you got the flux that you're actually looking for of the vector field is going to be, well, it's going to be 224 pi over 3, and we would have subtracted this flux integral over here, but it was just 0, so let's just call it 224 pi over 3. Alright, so that's the end of this set of questions, and hopefully this will help. This is very, very similar to the last two quizzes that y'all took, and so hopefully this will help you prepare for the test.